visually presenting our work towards generative class prompt learning for fine-grained visual recognition, accepted as an oral presentation in BMVC 2024. I'm Soumitri Chattopadhyay from the Department of Computer Science at University of North Carolina at Chapel Hill, and I'm accompanied by my co-authors Sanket Biswas and Josep Llados from the Computer Vision Center in Barcelona, Spain, and Emanuele Vivoli from the University of Florence, Italy. To give a quick overview of our work, we identify several limitations of CLIP, especially for unseen or fine-grained concepts, and try to mitigate them by proposing a generative few-shot class prompt learning setup that leverages pre-trained text-to-image diffusion models. We also show that our proposed approach outperforms several existing vision language tuning frameworks across many benchmark datasets. The driving motivation for this work is based on certain limitations observed in clip-based tuning approaches, which perform suboptimally on fine-grained datasets. Some of these fine-grained concepts are hard to describe by language, for example, fractal patterns and abstract imagery, and some categories being highly domain-specific, for example, vehicular models and aircraft models that you see in the slide, do not have enough semantic cues. Also, CLIP's knowledge is vastly based on natural visual content, and thus they cannot be directly adopted to unseen domains like medical imaging. We tackle these issues by leveraging generative models, especially text-to-image latent diffusion models, which have stronger visual linguistic synergy that can capture fine-grained visual information. Coming to the methodology, which is termed as GCPL or Generative Class Prompt Learning, we first parameterize the class token of a handcrafted prompt, making it learnable, and optimize it by the reconstruction loss of a frozen diffusion model, which is stable diffusion for our case, for which this prompt acts as an conditioning signal. This is done over few short support sets of each class and hence is on a per class basis. The class token is directly optimized by the feedback coming from the generation by the diffusion model. We further improve it by proposing COMPL or contrastive multiclass prompt learning that introduces a simple interclass contrastive constraint that enforces divergence of these denoised outputs across different classes, as shown in the figure. Finally, we plug in our learned class tokens and leverage a diffusion classifier framework during inference. Our competitors here are zero-shot methods such as clip classifier and diffusion classifier, and we also talk about a few-shot prompt learning and adaptive tuning techniques that have been proposed in literature. The figures show a schematic of these methods. Coming to the quantitative results, first we see that the zero-shot methods severely fail for unseen domains like medical images, while adapters are more effective for unseen domains, and they show low variance across random seeds. GCPL and COMPL still perform better than them. And coming to prompt learning methods, we see they are very noisy under unseen domains, evident from the high variance scores across random seeds, and GCPL and COMPL surpass them by pretty heavy margins. We also vary the number of shots across all of these data sets to see if there is any performance trend decreasing or changing. And we see that the performance is fairly consistent across varying the number of shots, and the performance is always consistent even in comparison to other existing works. Thus, to summarize, our generative class prompt learning learns stronger, fine-grained visual linguistic representations that not only work for fine-grained and abstract semantic domains, but also generalizes to domains unseen to CLIP, for instance, the medical imaging datasets. Our project page and the link to our archive have been provided for reference. Our email IDs are present in the slide, and thanks for watching this presentation.